In the last lesson, we talked about radiation and the different decay types. Now we will discuss what happens to radiation when it interacts with matter. When ionizing radiation passes through matter, it can cause ionizations and excitations. But what are those actually? Ionization occurs when an electron is kicked out from the electron shell, creating a positively charged atom, so an ion. In order to expel an electron from the electron shell, sufficient energy is needed. How much energy is needed to kick out an electron depends on the Z of the material. The higher the number of protons, the more energy will be needed. This means that a different amount of energy is needed to remove an electron from lead than from hydrogen isotopes. The required energy also depends on the electron shell where the electron is situated. The electrons in the electron shell closest to the nucleus would need much higher energy to be removed when compared to electrons situated in electron shells further away from the nucleus. Only radiation that is highly energetic can cause ionizations. The radiation that we come across in our daily life, like for instance light, microwaves, etc., is not ionizing radiation, except for UV light of certain energies, which is also able to induce ionizations. And besides ionizations, ionizing radiation will also lead to excitation of electrons. In this case, electrons are not removed from the atom, but excited to a higher energy level. These excited electrons will eventually de-excite, going back to their original levels. This de-excitation is accompanied by the emission of X-rays. Let's now talk about the interaction of different particles with matter, starting with alpha particles. Alpha particles are helium nuclei and are therefore rather heavy. This means that their paths will hardly be affected when moving through matter, resulting in straight paths as shown here in a cloud chamber. Alpha particles interact mostly with the electrons of the atoms and cause a lot of ionizations, which slows them down and limits their range to just a few centimeters in air. Beta- particles, on the other hand, have much less interactions, causing much less ionizations. Since beta- particles are electrons and therefore are very light, their path will be influenced by the interactions with other electrons, resulting in curved paths as shown here. Because the electrons are polyenergetic, they will have different ranges. How far electrons will travel depends on the maximum energy of the particles and can range from a few millimeters to a few meters in air. Beta plus particles have similar behavior as beta minus particles, except remember that they will undergo annihilation when they recombine with an electron, and therefore beta plus interactions will always be accompanied by the emission of 2 photons of 511 keV. An important phenomenon to consider when dealing with beta- particles is Bremsstrahlung. Bremsstrahlung occurs when an electron is slowed down by the nucleus of an atom. This slowing down causes loss of energy, which in turn leads to the emission of X-rays. Bremsstrahlung creation depends on the number of protons of the material with which the electron interacts, so the Z of the material. The higher the Z, the higher the chance that X-rays will be emitted. Also, the higher the energy of the beta- particle, the more Bremsstrahlung will be created. In general, we can expect Bremsstrahlung radiation to occur for heavy materials such as, for instance, lead and high-energy beta- particles. Lastly, we will talk about the interaction of gammas and X-rays with matter. Gammas and X-rays interact in the same way. They both hardly have any interaction with matter, leading to few ionization events. Also, we cannot really talk about a well-defined range when we talk about photons, since a gamma photon can be stopped by one or few interactions or not stopped at all. Therefore, we talk about the decrease of intensity of photon radiation when passing through different materials rather than a range. There are 3 primary ways in which gamma rays interact with matter, called the photoelectric effect, the Compton effect, and the pair production. You can see on this slide the so-called curtain diagram, which schematically shows the interactions of gammas with matter as function of Z and energy. It depicts when we expect certain interaction to be dominant. Let us start with the first type of interaction, the photoelectric effect. The photoelectric effect occurs when a photon gives all of its energy to an electron, which then leaves the atom. The chance of the photoelectric effect to occur is higher for low energies, so low energy photons are more likely to lead to the photoelectric effect. Also, the higher the Z, the higher the chance that the photon will transfer all of its energy to an electron. The second interaction is called the Compton effect. In this case, only part of the energy is transferred to an electron, and the original energy of the photon will be reduced. The Compton effect is usually the most likely to occur since the chance of this interaction is high for a broad range of Z and energies. Finally, we have pair production, which is the opposite of annihilation, namely a photon is converted to an electron and a positron. The pair production will only occur if the photon has an energy of at least 1022 keV and when it interacts with high Z materials. Pair production is therefore mostly expected for highly energetic photons. Now, let's compare the different types of radiation in terms of shielding, meaning what materials do we need to shield ourselves from radiation. You can see that alpha radiation is the easiest to stop. We just need a piece of paper for that. To shield ourselves from beta minus particles, we would need a bit of plastic. Gammas are the most difficult to stop. They might require thick and heavy materials with a high Z, such as lead or concrete. Thank you for watching this lesson. Next time, we will discuss how radiation can be detected, which is closely related to what you have learned today.